Hello, everybody. My name is Tatiana Dashevsky. I'm a senior manager. I'm the leader of data science team at T-Mobile. And before I jump into the talk, I would like to ask you, how many of you actually have to deal with data science? How many of you actually work on big data? Cool. How many of you know Spark or worked with Spark? Okay, good. So that might be relevant to you, which is good. I want to thank Jeff, because what Jeff talked about is actually, it's a big deal for data science when you come to scaling. And in fact, we picked this topic because of, I went to Spark Summit, and I went to training. It's called Spark, a production of machine learning using Spark machine learning algorithms. And it's all built in cloud. And I had a row of people sitting there and saying, okay, we are in big data and we actually work on-prem. How do we put this in production, and what are the challenges? So in that specific assignment, it wasn't addressed, but that's why I think I kind of wanted to bring it up. It's still there, and that's why we're going to talk about this today. So it's how do we put machine learning models into production on premises, and what's the challenges and how we address those. Okay, so that's just the list of the tools. Of course, it's not the whole picture, but I just want to say, okay, we do have cloud, we have on-premises, and we have standalone mode, which is personal device. And data scientists, especially in small startups with small companies, they use personal computers, they use Python, R Studio, and all these packages in Python, and very happy. And it's beautiful, I love it, and this is how I started. And then you have cloud, and usually cloud is pre-built. You have all these tools, and we have AWS, we have Azure, we have Google Cloud. Google Cloud is trying to catch up, but it's not there, of course. I mean, if you look at the pricing, you would be not surprised, and the privacy policy. So we have this AWS and Azure, and Azure did a very smart move. They incorporated Databricks. And Databricks is what data scientists like. It's very similar to Jupyter, it's very familiar, and Databricks builds all these tools. It has Spark, it has Python, it has everything. So that's, but the question is, how do we actually replicate similar thing on-prem? So that's, because those are open source tools. You can get Spark, you can get all these libraries, MLlib, everything is there. So that's for example, the system. You have HDFS, it's a file system, and you have Yarn, and you have all this MapReduce, Test, Spark, Storm. Storm is for streaming, Spark is for machine learning, Test and MapReduce is for Hive. And for people who likes to do analytics and just likes SQL. For someone who likes machine learning, that's the only available tool in big data is Spark. That's why it's took off so fast, because you cannot really use Python in a big data. Okay, so let's just talk a little bit more about machine learning algorithm. And the reason why I brought up the slide here, it's just kind of get you the idea. If you're not familiar with PySpark, or pretty much PySpark, it's a Python API for Spark. It will be still very easy for you to transition if you know Python. And that was a very smart move from Databricks, because they knew that Python community is huge. So they just took the schema, I would say, and implemented this. So you have, if you see, you have the same structure. If you're trying to run the machine learning model, you have to load the data, that you have to do the data split, then you need to train, feed, and train the model, and predict. In PySpark, you have stages, and usually the bit pipeline. You can do this in Python, but it's already pre-built in PySpark. You have pipeline, and then you load the data, you do this data split, you do vector assembler. It's just the way how you engineer the data, and then you do exactly the same, feed and predict. Very easy to transition, and if you look at here, you probably don't see the typing here, but it's like even the language is very similar. Import from PySpark, import whatever, classification model, random forest classifier, the same random forest you can get classifier, very similar, which is easy to transition. That's why I think I don't really want to talk about this specific issue, because MLlib is a well-known library. You can just go and play. So what I want to talk about this, it's the problem itself MLlib has. It's wonderful, great, I like it, but it's limited. Python is huge, and because it's existed for a longer period, the libraries are massive, and Python MLlib is trying to catch up, but it's not there yet. So what do you have to do? Oh, then let me actually, before I jump into user-defined function, I want to talk about what Jeff was saying is Spark. And one of the, I would say, advantage of working on-prem for data scientists is actually you know the backend. You know what's going on under the hood. Because when you work on cloud, what I noticed, like data scientists, they just never care. OK, this is the number of executors I have. I have like 4 or 5 cores. I don't care. But it runs. It spins. I get that. And it's great. We never think about what is under the hood and how we have to optimize the model. When you work on-prem, you do have to think, because you share environment with other. If I submit my job and if I ask for 1,000 executors, my neighbor is going to tell me, hey, Tatiana, what are you doing? Like, I can run my jobs. You took too much memory. You took the entire, all the cores I have. So that's why you have to Spark ML job when you submit it. And here, there's 3 main points when the data scientists have to think when they work. It's dynamic allocation versus static. I personally like the idea of dynamic allocation, is great, but if I need to get the work done, I prefer static. Because when you submit the job, static, you say, I need 1,000 executors, each executor is 3 gigabytes. It gives you right away, it's allocated. Here, it's yours. With dynamic, it starts releasing slowly. It takes you, gives you, let's say, 100 executors, and that starts building based on the demand. And that's pretty much what you see. The good thing about dynamic allocation, once you're done with calculation, it starts releasing the executors, releasing the memory, so that other users can come and catch it and get the executors, use the memory on the node. Because a lot of users, if they use static allocation, they just forget to, say, close the job. And you go home. So what could happen is just you allocated this source, you've done your calculation, but still your account stored this, like, let's say, 50 nodes, and nobody can use it. So that's the big disadvantage. So you have to be careful when you think. But again, that's the speed. Other thing, multi-core versus number of executors. Very important features for data scientists, because if you put the model into production, you have to think, what do you want? Do you want your job get done fast? If that's about time, then you have to think how many threads you need to have. You need to have as many threads as you can, parallelize your job. That comes from your configuration again. The thread, number of threads, it's number of executors plus number of cores. This is pretty much math behind there. So number of cores define how many cores your machine has. Each machine usually has 64 cores. So it means for instance, my machine learning job, when I look at what I do, it says, oh, I need 5 core. That's just optimization. It means I can have only 12 executors, approximately 12 executors per machine. But then you have to think again, I want to use the entire resources in my node. I don't want to have any leftovers. I want to use the whole memory. So you have some leftovers for driver memory, but then again, you take the entire memory of 256 divided by 12, so approximately you put the settings. So for data scientists, when you submit a job, it is kind of important, because then it's what defines how job, if it gets done fast, and also helps to not be greedy with the resources. Use what you need, and that's it. The last part, what I kind of want to bring up it could be important. When you run jobs in Spark, very cool function is actually Coalesce and Repartition. So when you want to get your job done fast, you want to have a lot of threads. You get a lot of threads, let's say 1,000. And then eventually you have the algorithm which is done. Let's say graph, for instance. We just ran recently graph analytics. OK, I got 2,000 threads. I want to save it. I got 2,000 CSV files. That's how Spark works. So if you don't want to have this, because if you want to then read the output, it's going to read 2,000 files. It's going to take a lot of time. So to get that, you have to just coalesce. What it does, it shrinks down everything to one partition. This is the number of partitions, number of threads. So it shrinks it, and then instead of 2,000 files, you get 1 file. The same thing when you actually want to speed up, increase the performance, you just have to repartition and increase, let's say, number of threads with the repartition function. OK, that's the kind of the message what you have to consider when you submit the Spark jobs. The next one is, again, kind of trying to convince you, even if you're not in big data environment, why it's still kind of fun and good to use PySpark versus Python. So I think first message was that I would prefer to use PySpark just because it's faster. But the challenge is, and I hear it all the time, Spark ML or MLlib doesn't have enough libraries. So what do we do about this? We create UDF, user-defined functions. And it's a painful, but again, it's a great and fun challenge for data scientists, because then you have to be creative and create your own functions. So, but let's look at this example specifically. It's a standalone mode. This is on my computer. And I already preloaded the Jupyter here. So I'm just going to share the output, so just to keep the time. So here, this is just on my computer. There is no, right now on-prem, this is standalone Spark on Mac. And so that's, if someone who is not familiar, this is just you load the function by Spark. This is your Python. Everybody knows this. This is how you actually configure the Spark. It's, it's kind of easy to do. But look at this. So I have a file, this file. I saved the file, and this specific, it's like 400 megabytes, not big, but for the computer to read in Panda, it's actually big. So let's see if I have timing for this. I don't, yeah, okay, so for this, probably here. If you look at the timing, for instance, look at this. This is the load in time. I just ran it, and like pretty much you do read CSV file 400 gigs, and you see it takes 10 seconds. But it's CPU time 10 seconds. So look at PySpark. It takes CPU time 2.5 milliseconds, system 2 milliseconds, total 4.45 milliseconds. It's just the performance. It's absolutely amazing. It's so fast because, and then I'll go next to this one. Because what it does, it's not just loading into one object. You have executors, and it does parallel computing. So even if you're a Python user, and you sometimes have big files, you don't want to waste like a couple hours. You can just set up PySpark, and it's going to take you like 30 minutes or less, 15 minutes to get the work done. OK, so next, this is how you actually do the user-defined function. So I got this function. This one is Approximate Entropy here. So what this I just copy and paste from Wikipedia. And what Approximate Entropy is quite an interesting function. It helps to detect anomalies in time series data. It's used in medicine a lot. It's also used for detecting anomalies in time series data, any type of anomalies. But usually, if your entropy is very low for that specific case, then it is very periodic. And in human body, it means bad. And that's, for example, how you can predict the heart failure. Because if it becomes very periodic, you most likely you're going to have a heart attack or something like that. But the same with respiration. So just for fun, you have this, and in Python it's open source. It's great. It works. So look at this. I took the small data set. It's only this specific data set. It's not 400 megabytes. It's 1,000 rows. It's a dummy data set, time series data. And if you look at CPU, it's you load the functions 5.whatever, almost 6 seconds. And then you do the same with PySpark UDF. What it does tells you the CPU time is 19.5 milliseconds. So totally it just outperforms even if you do user-defined function in PySpark. So great, but what do I do if I have more than 2 gigabytes? Python usually handles, 2 to 4 gigabytes of data. What if we actually work with something else, like this one? So this is just, for instance, number of records. 3.8 approximate billion, so I have 115 gigabytes of data. Well, Python say bye-bye because you cannot really do anything. So now let's compare PySpark UDF versus PySpark. And again, just think of this, how PySpark UDF of Python function does. It has a Python function, and on top of this, it's a wrapper for Python. But then you also have a PySpark functions when you can write your own, so you don't use under hood Python. You actually work with data frames. And interesting, what it does, it actually outperforms. And it really depends on what kind of task you do. For instance, this one, you see, this is just a simple use case. You have big data sets. You just want to get the phone numbers that have, that specific pattern. What is this pattern? Like 900. So use just a regex. That's your function, and you do the wrapper, and then this is just PySpark function regex. And it's outperformed. So PySpark actually takes under the minute, and then if you do PySpark UDF, 2.2. So you still have to, if you care about the performance, you would prefer not to do PySpark UDF. You will just probably go with PySpark. Would you write your own function using data frames? Because data frames, the way how they build, it doesn't use serialization, deserialization. And you lose time on that. Because under the hood, when you use RDD, you actually have to serialize and deserialize the data. And that sometimes takes time. And that's why performance could be a little bit slower. OK, so next. OK, and speaking of the production, because here we mentioned, OK, how do we production? In cloud, it's easy. You have AutoML, you have MLflow. It's a new package. Here's the same idea. On-prem, but you have to build your own. And the same, you got the data, you have the data quality, you make check, and then you have alert system. Alert system talks to this. You need to make sure everything is good with data. You check null, you check duplicates, you address non-values, you address outliers. Then you do feature engineering. And again, feature engineering, you watch for data drifting. There is a functions for data drifting in Python. Unfortunately, you don't have this function in PySpark, so you have to write your own. A lot of creativity for data scientists right there. So it goes again in the alert system, and then you build the model. Again, the model also needs to have some kind of definition of the drifting. If the model is actually starts drifting, you have to retrain. Because some, I've noticed that some practice, I'm going to retrain the model every month, or I'm going to retrain the model every week. What's the point? You have to retrain when it's needed, so that's why it's good to actually see when your data gets drifted and when your model actually gets drifted. And then you put this as a part of the automation. Then you put everything into the report, and the report constantly talks with the alert system. That's your pretty much the same schema as MLflow or AutoML, how you put this in production, but on-prem. OK, take-home messages here for data scientists. ML jobs on premises require Spark configuration, tuning. And I highly encourage actually to do that because it's also science. Tuning Spark is kind of science because you have to think as an alternative way to tune your configuration so that your algorithm talks to memory, talks to your CPU. And then it's fun because you learn something new. Then MLlib is limited, so as alternative, you can create your user-defined function via Python, using Python. But if you have massive data like terabytes, just stay away from this and write your own and using PySpark data frames. That's it. Thank you very much. If you have any questions, I think we still have some time.